So far, what we've seen in our chemical bonding unit is that we know a little bit about bonding theory. Now, bonds are all to do with our valence electrons in our outermost energy level. We've seen how those valence electrons interact to form Lewis diagrams. Now, what you might notice with those Lewis diagrams is we've only really dealt with molecular compounds. So that's when we've looked a little bit deeper into explaining our molecular compounds and explaining the concept of our covalent bonds and how those electrons are shared. Now, we also looked a little bit about representing our molecules as either a Lewis formula, a structural formula, or a stereochemical formula, and we're going to get a little bit more into our stereochemistry in this lesson, okay? But we've also taken a look at the difference between our empirical and molecular formulas. Now, as we continue on, we are going to see a little bit more about this molecular geometry because we have a specific way of drawing out our molecules now, and we will look at how we can determine other concepts that are important to molecules. And then, like I mentioned in our last video, we're going to jump back to more of our ionic compounds and some other molecular compounds to do with solid entities. So right now we're going to jump into this molecular geometry, which is an interesting concept, and it often involves quite a bit of practice and studying to really understand this molecular geometry. So at this point, I would really recommend pulling out a notebook, pulling out a pencil, and jotting down some notes because it will be very helpful as we go through. So we can start to identify different molecules as having a particular shape. Now, our molecular shapes in this chemistry course, we look at basically 5 different molecular shapes, which we'll get into in a minute. Now, we call this theory of determining what shape a molecule exhibits VSEPR. Now, this theory is called valence shell electron pair repulsion, meaning VSEPR. That's our abbreviation. Now, I want you to keep in mind that we're talking about electron pair repulsion. Now, when we break this down, we're talking about valence shell electrons, which is our bonding electrons, or any electrons that could be involved in a bond. However, we also have pairs of electrons. Now, so far, the pairs of electrons that we are aware of is either lone pairs or bonding pairs. So we've seen how we have bonds in between 2 elements, or we have those pairs of electrons that surround our elements. Usually it's a peripheral atom, sometimes it's our central atom, but those lone pairs and bonding pairs will repel each other. It's repulsion. They don't want to be close to each other, which makes sense. There's a bunch of negative charge. Oh, how did I skip so far? There's a bunch of negative charges that don't like to be close to each other. So our VSEPR theory is based on the electrical repulsion or charge repulsion of bonded and unbonded electron pairs in a molecule, which is what we've just basically dissected from our definition there. Now, stereochemistry, as you might recall from our last lesson, is the 3D arrangement of our molecules. Okay, and this really affects how a chemical does react with another chemical. So the stereochemistry is important as we go through. Now, again, this stereochemistry is our 3 dimensions, and if we can recall our 3 dimensions, we always start with our x and our y, so we have x and our y. But we also have this 3rd dimension, which is our z dimension, and you picture that as going into the page or coming out from the page. So we have 3 dimensions, x, y, and z. So our molecular shapes, according to VSEPR theory, only the valence electrons of the central atoms. Let's underline that, central atoms. Why is this jumping across on me? There we go. So our central atoms are only important for molecular shape. Now, that is an important thing to notice. We only really look at those electron pairs, so either our lone pairs, and I'm just going to abbreviate that as LP, our lone pairs or our bonding pairs, and I'm going to abbreviate that as BP, those are the only electrons around that central atom that really play a part in the shape of the molecule. Now, our valence electrons are paired in a molecule or polyatomic ion, which we know is either lone pairs or bonding pairs. Bonded pairs of electrons and lone pairs of electrons are treated approximately equally. Now, I'm going to use that word approximately equally because we do notice that our lone pairs exhibit a slightly greater push or repulsion from our bonding electrons. Now, our valence electron pairs repel each other electrostatically, which means that negative charges don't like to be beside each other, so they repel. And molecular shape is determined by the positions of the electron pairs when they're a maximum distance away. So essentially, the electrons are naturally going to repel each other a maximum distance when there's a certain number of electrons around it. So just like if you have two positive ends of a magnet or two north ends of a magnet, you'll basically, if you bring them together, there's a maximum distance that will like to repel each other, and when you have more magnets, if you were to add another north end of a magnet, then you may have greater repulsion. So we want all of our electron pairs to be the maximum distance away from each other. Now, there's essentially 5 molecular shapes. There's a linear straight shape, trigonal planar, tetrahedral, trigonal pyramidal, and angular or V-shaped. Now, we call this angular, V-shaped. Sometimes we call it bent. Okay, but essentially it's exactly what it sounds like. It's a V shape. So our linear kind of looks like this. All right, this is just in very, very general. Trigonal planar, trigonal. Okay, tri meaning 3. Planar meaning in a single plane. So what that means is we have a molecular shape that maybe looks something like this. They're all still in the XY. There's nothing coming out at you. Okay, tetrahedral is 4, tetra meaning 4, but we have some of these coming at you, and let me fix that here. Tetrahedral would be 4, and we have a Y and an X, and then we also have this Z component in there. So we have an X and a Y and a Z. Trigonal pyramidal, again, we have a tri, and we have a pyramid shape. So we have an X and a Y, and actually we still have a Z component. Okay, so we have three elements potentially, and it's in that sort of pyramid shape. Then we have our bent shape, which is literally just the shape as it describes. I'm going to draw that a little bit nicer. It is a V shape like so in 2 dimensions. So really what we see is there's only 2 shapes that really exhibit a 3-dimensional shape. Well, these ones are also 3-dimensional. We can rotate the shape and whatever, but that actually has 3-dimensional components is our tetrahedral and trigonal planar, which we'll get, trigonal pyramidal, which we'll get into here in a second. So these are our 5 molecular shapes that we're concerned with in Chemistry 20. Now, multiple bonds in VSEPR, we've learned about how if we have extra electrons being shared between a central atom and a peripheral atom, like we've seen in our Lewis diagrams, we know that our multiple bond in VSEPR theory, so valence shell electron pair repulsion, is considered exactly the same way as a single bond. So if we have a double bond like this, okay, this is equivalent, and we treat it identical to a single bond. So if we are looking at the number of bonds, this is equal to 1 bond, and this is equal to 1 bond. Just because we call this a double bond doesn't mean that there's 2 bonds present. It's 1 bond that is just a little bit shorter and stronger than a single bond. Okay, but this is still equivalent to 1 bond and 1 bond. That is very important to note as we move forward. Same with a triple bond. It's still, there might be more electrons, but it's still considered a single one bond, okay? So they're treated the same way as single bonds, which we've mentioned. So molecular shapes, we are going to start with linear, and we're going to try and go through this to make sure that it's clear as to where we get this molecular shape from, and we're going to try and derive a general formula that will maybe help us as we go through this unit to figure out our molecular shapes. So let's just begin, and we're going to take a look at beryllium dihydride. So let's start by writing out our symbol, beryllium dihydride. So we have BeH2, and we'll take a look at the other example here as well, where we have hydrogen fluoride, which is HF. Now, I have two examples here because there is kind of two general formulas for our linear shape, but I'm going to go through each example individually and we'll make a little bit more sense of this. So if we were to draw out our Lewis diagram for beryllium dihydride, we might need to take a look to see how many valence electrons beryllium and hydrogen have. So let's jump over to our periodic table, and we see that beryllium has, sorry, I've skipped it here. Let me just erase some of this. Oh, we're good. Okay, beryllium has 2 electrons and hydrogen has 1 each, meaning that we have 4 total electrons to deal with. So if we look at our drawing, we have beryllium, that's boron, beryllium, and we have 2 hydrogens. Now we only have 4 electrons to deal with, so we go 1, 2, 3, 4, and this is a full valence for our hydrogens, but beryllium is unhappy. Now, this is simply because our beryllium does not follow our octet rule. So what we can take a look at is the number of bond pairs on beryllium, because remember, we only look at our central atom. We're only concerned with the electrons paired around our central atom. We have 2 bond pairs. Now, if we look at our lone pairs, there's no lone pairs. There's no pairs of electrons that don't exist between the central atom and the peripheral atom. So the lone pairs is 0. Now, the general formula that we come up with for this is going to be based on a few things. In general, we call A as our central atom. Okay, we call X as our peripheral atoms. And we call E as any lone pairs. Okay, that will help us to determine these general formulas. So, when I look at my central atom, okay, I have only a single central atom, so I notate that as A. I have 2 peripheral atoms, so I identify that as X, but because I have 2, I have to say AX2. Now, either I can say AX2E0, or I can simply leave it as just AX2. So maybe in brackets, what I'll do down here is I'll say, oh, let me do this in a different color, E0. Okay, generally in this case, our general formula would be AX2. Now, our stereochemistry is linear. So if I was to draw my example out here, I would draw it out as beryllium with our 2 hydrogens in a nice straight line. Okay, that is a linear molecule. Our molecular shape is linear and it exists in 2 dimensions. Okay, if we look at our next example of hydrogen fluoride Fluoride has 7 electrons, hydrogen has 1, giving us a total of 8 electrons. So, because our bonding capacity of each of these is just 1, it doesn't really matter which element we have as our central atom, but generally I never choose hydrogen as my central atom. So I have fluorine and I have hydrogen. So I have hydrogen fluoride, and I start by putting my bonding electrons in. And then if I go around and I place the remaining 6 electrons, they exist around my fluorine. So the number of bonding pairs that I have in this case is only 1. Oops. Okay, so I have 1 bonding pair. And when I look at the lone pairs around my central atom, because hydrogen is never my central atom, I see that I have 3 sets of lone pairs around my central atom. Okay, again, we're only looking at our central atom geometry. That's the only part that is important. So when I go to write out this general formula, I would write it as I have a single X, only 1, so I only need to write 1 down. I don't need to put the subscript there. E, and I have 3 lone pairs, so I have AXE3. So when I draw this out, my stereochemical formula is still linear, but because I don't need to indicate my lone pairs, I have hydrogen fluoride like so. Okay, so I see that my stereochemistry for both of these examples is linear. However, I have 2 separate general formulas that can derive a linear molecular or a linear molecular shape, and the stereochemistry is linear for both of these examples. If we take a look at our next example, which is angular, now remember this is angular, bent, V-shaped. Those words are all interchangeable there. If we look at our example of water, which is H2O, okay, we're going to count the number of bond pairs and electron pairs. Now this time I'm going to draw, I have some space at the bottom here, so I'm going to draw this out. So oxygen has 6 valence electrons, and each hydrogen has 1, so that gives me 2 electrons, so it has a total of 8 electrons to place. Now, because my central atom is going to be oxygen, it has a greater bonding capacity. I'm going to place my 2 hydrogens around that. And I start by placing the bonds first. 1, 2, 3, 4. I've used up 4 electrons, giving me 4 electrons to place. Now because my hydrogens are happy with 2 electrons, they've completed their octet with 2, then I go 1, 2, 3, 4, and I've used up all of my electrons, and oxygen now has a happy octet. Now when I look at my bond pairs, I see that I have 2 bond pairs, so I have 2 bond pairs, and I have 2 lone pairs. Okay, my general formula is that I have a single central atom. Now what colors did I do here? I have a single central atom, so I have A. I have 2 peripheral atoms, and I have 2 lone pairs. So 2 peripheral atoms and 2 lone pairs gives me a bent or angular shape. Now when I go to draw this out, what happens is that these 2 lone pairs like to push on these electron pairs a little bit stronger than these guys will push towards each other. So when I create my shape, it's actually a V shape, and my electron pairs, now if I was to draw this out with my geometry, it would look something like this. And I'm going to do the in-between with my electron pairs on top here. But these 2 electron pairs, again, are pushing away from each other pretty strongly, and they're pushing down on these guys fairly strongly, okay, resulting in this angular shape, like so. Okay, so I have my angular or V-shaped stereochemistry, and again, this is in 2 dimensions. We have it in the X and the Y. You can call this Y and this X, whatever you like. Okay, but essentially this is my stereochemistry. The shape is a V-shaped. Okay, now if I take a look at my next shape, I have my trigonal planar. Notice again, I have this tri meaning 3. So maybe that means 3 central atoms, maybe it means 3 peripheral atoms, maybe it means 3 bonding pairs. We're going to take a look at what that means. So I have boron trihydride. So if I write that out, I have boron trihydride, like so. Again, my boron, when I check out my periodic table, boron Boron has 3 electrons, and I have 3 hydrogens, each containing 1, so I have 3 electrons to deal with, giving me 6 electrons total to work with. Now I know boron is my central atom because hydrogen is never my central atom, and I start by placing my hydrogens around that. I know that it can exist in sort of one of 4 orbitals that surround this invisible box around my boron. And I start by placing those electrons. 1, 2, 3, 4, 5, 6. Well, there we go. I've used up all of my electrons, so there's no more left to place. So when I go and jot down what I have 3 bond pairs and 0 lone pairs. So when I go to write my general formula, I have AX3. I don't have any lone pairs, so because of that, I simply just have AX3. I don't need to include that E. Again, I can include the E in the bottom in brackets, E is 0, but I just don't need to include that in there. Now, because these electrons are going to repel each other as best as they can, these guys are going to want to have an equal space between these ones and these ones. Well, you'll notice that the space between my left and right hydrogens are pretty far apart. So I want to try and space those as far apart as they can. So when I go to draw this, it's kind of going to look like a peace sign. And I'm going to try and draw these angles as far apart and as equal as I can. Now, my drawings aren't perfect in terms of chemistry, but that's kind of gives you a better idea. Now notice that because these guys are all repelling each other, and they're all sort of rotating around the same center point, that there's no component or no element that's jumping out of the page at you. They're all in the same plane. Okay, they're all in the XY dimension or plane. So when we have trigonal, planar, we're talking about we have 3 bonding pairs, or you can consider that as 3 peripheral atoms that are all in the same plane. Okay, they're all existing in that sort of singular 2-dimension on your page. Okay, the plane on your page is the plane that it exists on. Okay, so our general formula is AX3. Let's take a look at another example. We have trigonal pyramidal. Now again, notice we have tri, and we have a pyramid this time. So let's take a look at what that might mean. Ammonia. Our example with ammonia is NH3. So ammonia, our nitrogen contributes 5 electrons, and we have 3 hydrogens contributing each 1, giving us 3 electrons, giving us a total of 8 electrons. So we draw out our central atom, and we draw our peripheral atoms around it from our Lewis structures, which we should be now pros at. So I've placed 6 electrons because I need my bonds to have 2 electrons each. Now because hydrogen is happy with 2 electrons in its octet, our remaining 2 electrons get placed on our nitrogen. Okay. Now what you might think here is that there's 4 bonds, but really when we look, we only have 3 bonds and a single lone pair, but we have 4 pairs of electrons, which can be confusing when we look at our next example, but do not get confused. We have only 3 bonds, and we have 1 lone pair. Remember, we're only looking at our bonds and lone pairs around our central atom. That I cannot stress that more. You can get really confused if you end up counting all of your bonds. Now our general formula for this, we have one central atom again. We have 3 peripheral atoms, or 3 bonding electrons, or bonding pairs, I should say. And we have 1 lone pair. So again, because this lone pair is kind of pushing harder down on our 3 bonding pairs, we get this shape where our hydrogens are kind of bent down towards our nitrogen. So when we draw that, we have our nitrogen, and we can have 2 hydrogens that exist in the plane of the page, so we can draw them as just straight lines. But we also have 1 hydrogen that's kind of coming out towards us, or if I was to rotate this molecule, if you can picture turning a molecule, or if you put your pointer finger, your middle finger, and your thumb out and downwards, kind of in front of you, and you rotate your hand so that your thumb is pointing towards you. Okay, you can also rotate your hand so your thumb is pointing away from you. There's still your pointer finger and your middle finger that kind of stay on the same plane. So that's why we can draw them as either a straight line, or if I wanted, I can even make this one coming away from me or towards me. But as long as I have 2 that exist in one plane and 1 that exists in a plane that's coming out towards you or something like that, then you should be good with your stereochemistry. Notice that this is a 3-dimensional molecule. It exists in 3 dimensions. Again, this number of bond pairs and number of lone pairs tells us our general formula, and it also tells us our stereochemistry. It also tells us that we have this trigonal pyramidal. And again, we create this pyramidal shape because this lone pair repels those bonding pairs a little bit stronger, kind of flopping them down around that nitrogen. I'm just going to save my text here so I don't lose any of it. If we take a look at our last example, I believe, oopsies, what's going on here? Okay, our last example in terms of determining our molecular shape here, we're going to look at methane. So we have CH4. Again, each carbon contributes 4 electrons. Each hydrogen contributes 1. We have 4 of them, so that's another 4 electrons, giving us a total of 8 electrons. When I place my central atom, I draw my peripheral atoms surrounding that, 1 sort of in each orbital. Again, our invisible box around our carbon. And I place my 8 electrons. I've used up all 8. There's none left behind. Therefore, that is my total Lewis structure. Now, when I look at my bond pairs, I see that I have 4 bond pairs. I have 0 lone pairs. And my general formula would be 1 central atom, A, X, 4. And again, I don't need to put this in there. I'm just going to jot it down in brackets underneath. I have E0. And our stereochemistry is tetrahedral. Tetra meaning 4. Okay, and hedral is sort of a general shape that we exhibit. Now, we have our stereochemistry existing in, again, a 3-dimension type drawing where we have 2 hydrogens existing in the X and Y plane and 2 existing in sort of that Z plane, you can kind of think of it. So we have 1 that's coming away, going away from you, and 1 that's sort of coming towards you. And you picture this if your pencil is going into the screen, okay, that you have a 3-dimensional shape. This is your stereochemistry of your tetrahedral molecule. So now that we've looked at all 5 shapes, we've looked at linear, we've looked at bent, trigonal planar, trigonal pyramidal, and tetrahedral, we're going to look at a few other examples where we need to determine these molecular shapes. So let's take a look at ClO2. Now I see that O is going to be my central atom. Oxygen has 6 electrons, chlorine has 7 each, so there's 14 plus 6, which is 20 electrons. start by drawing my oxygen. I better give myself some room here. Oxygen, I have my 2 chlorines surrounding that. What colors? Oh yeah, so chlorine and chlorine. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So because I have my 20 electrons that are placed in this formation, notice I have 2 lone pairs and I have 2 bonding pairs, which gives me a bent shape. So I only know that because I've just written down that my bent or angular shape, oops, I'm drawing the wrong molecule here, drawing water. I know that it's going to exhibit this molecular shape because I've just written down that my general formula for a bent shape is AX2E2. Or, if I don't like to remember it that way, 2 lone pairs, 2 bonding pairs equals a bent shape. Let's take a look at our next example. I know sulfur is going to be our central atom. Think of it as my body and my 2 arms, okay? I have my center of my body and my 2 arms are on the periphery of my body. So sulfur contributes 6 electrons, hydrogen contributes 1 each, making a total of 8. So I draw my sulfur, draw my hydrogens. I have 1, 2, 3, 4, 5, 6, 7, 8. Again, hydrogen's happy with 2 electrons in its octet. Again, 2 lone pairs, 2 bonding pairs, giving me a bent molecular shape. Oops, I've done that all backwards. There we go. Okay, BBr3, boron contributes 3 electrons, bromine each contributes 7. So 7 times 3 is 21, plus our 3, which would be 26 electrons. So I know that I have 1 body and I could have 3 limbs, okay, but my center of my body is going to be my central atom, so my boron. I have Br, Br, Br. And I start placing my electrons in my bonds first. I've used up 6. Then I start placing them on my peripheral atoms. So 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So I've used up, all 24 electrons that I have, because again, 21 electrons from bromine, and 3 from boron, which gives me 24 total electrons. And what I get here is I get my central atom with my 3, I only have 3 bonding pairs, okay, no lone pairs. Again, we're only concerned with our central atom, so I get a shape that looks like this. Okay, if I look at SiF4, or silicon tetrafluoride, again, 1 body, 4 limbs. Silicon contributes 4 electrons, fluorine contributes 7 each, so we have 28 electrons to deal with. Sorry, that's wrong. 32 electrons to deal with. I'm going to have to squish this guy in here. Immediately when I see this, I automatically start to think, hey, I have 4 elements surrounding my central atom, and 4 elements usually results in 4 bonding pairs, which would indicate this would be a tetrahedral molecule, but I'll continue on just to make sure. I see that I have 4 bonding pairs, which means that I have a tetrahedral molecule, and I would draw that something like this. Oops. Something like so for my tetrahedral molecule, tetrahedral shape. Again, 4 bonding pairs, no lone pairs, giving me a tetrahedral shape. Okay, BrO3. I have 3 oxygens, each contributing 6 electrons, giving me 8, plus my single electron here, which is 9, plus my bromine contributes 7, giving me a total of 16 electrons. So again, my bromine looks like it might be my central atom, okay, but let's take a look. Bromine, my oxygens surrounding that. Again, because I have a molecule when I have covalent bonds, it doesn't really matter how my electrons are shared within that molecule. So it shouldn't matter too much here as we go through this example. So again, place my electrons 1, 2, 3, 4, 5, 6. Okay, then I do my peripheral atoms. 10, 12, 14, 16, 18, 20, 22, 24. Now, I can't remember how many I said I had. 18, 19, and 7, so 26. So then I place this last guy on the top there. So what I see here is I have 1 lone pair and 3 bonding pairs. Now 1 lone pair, 3 bonding pairs. I see that this lone pair is probably going to push these guys a little harder, which means that I would get a tetrahedral shape. So I would get something like this. O. And again, because this is an ion, I should probably put my square brackets with my charge along the outside. Last example we'll take a look at is our ammonium ion. Nitrogen contributes 5, each hydrogen contributes 1, giving us a total of 9, but notice it's a positive charge, so we have to take away 1 electron, giving us 8 total electrons. Our central atom will be nitrogen, 1 body, 4 limbs. Place my peripheral atoms around, 8 electrons. All 8 electrons will exist in our bonds, making a complete octet for all of our atoms there. Notice that they are all existing in bonding electrons or bonding pairs. So when I go to draw this out, again, this is going to be a 3-dimensional and again, polyatomic ion, I will exhibit my charge on the outside of those brackets. Now again, this is a concept that you have to be very practiced in to not have to consistently refer to a chart with your information in it. So the one thing you may want to notice is that when we look at electrons, when we look at the total number of electron pairs, if we have 4 electron pairs sort of surrounding that molecule, we see that we have what we consider sort of a tetrahedral electron pairs, but we are very specific when we look at the difference between our bonding electrons and our lone pair electrons. Okay, because there is a slightly different shape due to our lone pair electrons forcing the ions or the atoms downwards, we get a different molecular shape for each of our examples. So it is very important to start to be familiar that if there's 3 bonding pairs and 1 lone pair, you get a trigonal pyramidal. If you have 3 bonding pairs, no lone pairs, trigonal planar. 4 bonding pairs would be tetrahedral. 2 lone pairs, 2 bonding pairs is angular or bent. And then if we have a linear molecule, it's either 1 bonding pair and 3 lone pairs, or we have 2 bonding pairs total. So you should be getting practiced up with these shapes. There is an assignment to follow this lesson, and good luck.